we have, okay, yep, it's recording. Great. Okay, so welcome everyone to our SkyFit2 tutorial. The first tutorial about how to make an astrometric plate with our RMS tool has been published about 2 years ago. And since then, we made many changes. There's significant progress both in ease of software use, user friendliness, and of course, data quality. And we felt that it was necessary to make one more tutorial so we can show you what the improvements are, and so you can know how to use these tools, and you have the power to own and manipulate your own data. I think that's the most important part. Okay, so why are we even focusing on the astrometric calibration? Why is it so important? Well, it actually makes a huge difference. So it is the reason why RMS is doing so well, the Global Meteor Network is doing so well, and it makes a difference between, say, a fancy toy that makes pretty pictures and a scientific instrument. You simply cannot have good science-grade data if you don't have a good calibration. And that's why we put a lot of focus on it. And what we found in previous data, people are like, oh yeah, I just made it, sort of a plate, it's good, I'm just going to put it there and it's fine, it's working great. We found that is not the case. It really needs to be done well, it needs to be constantly recalibrated, and you need to know what you're doing. So the essential problem that an astrometric calibration is trying to solve is, how do you map image coordinates? So you have an image with stars with the meteor, and how do you map that onto a celestial sphere, right? Onto the sky to get some sort of right ascension coordinates or azimuth, altitude, time, whatever. So that is the main goal of an astrometric calibration. And the way we do it is actually, I would say in theory, quite simple. Let me just share my screen. So the way we make the calibration is basically you're trying to project something on the celestial sphere onto an image plane, right? Because your sensor is flat and it's nothing but a projection, a spherical projection onto a plane. And mathematically, that's not that complicated. There's a little couple of equations that are doing it. Here are the actual equations in our code that you can see that are doing this projection. Okay, so mass. What is then the issue? What's so hard? Well, this is the ideal case if you didn't have any lens distortion. You would basically then have to fit 5 parameters. You would have to fit the right ascension and declination of the center of the field of view. You would have to fit the rotation, and you would have to fit the scale, right? And sorry, that's 4 parameters, right? So you have that describes the pointing coordinates. But the problem is that most lenses have significant distortion. I can show you how this distortion looks like and what are some usual models. So if you had no distortion, any lines on the celestial sphere, if you project them onto the image plane, it would just be straight lines. But the truth is, you have lenses that have a barrel distortion that are kind of enlarging the central part and making the edges smaller, or the other way around. That's the pincushion distortion, where the center is smaller and the stuff at the edges is larger. Or you have a mustache distortion, which is a combination of two, where you have the center is enlarged, and then the stuff in the middle is smaller, and then the edges are enlarged again. And I can show this in practice. If you look at different models of distortion, this is basically how it looks like. So what we need to do then is find some sort of a mathematical model that describes these types of distortions and corrects for them. So then you can take your image pixel and project it onto the celestial sphere, and you know exactly where it is. And of course, the other way around, right? So we're actually using this reverse mapping to make the calibration, because we know where the stars should be on the sky. And the idea is to align the stars with the image, with the stars where they are on the image, and then kind of compute that mapping, right? And in theory, that's basically it. And as I said, of course, in practice, things are a bit more complicated. But before we get on the actual calibration, there are a couple of other things that I want to say, and that's how do we make the initial setup so the measurements are as precise as possible. And I like to talk about how to properly measure the location of your camera and put it in the config file. So most people use their phone GPS devices to measure the location of the camera, and they are fairly accurate. But the problem is any GPS device has issues with properly measuring the elevation. And the reason is simple. The GPS satellites that your phone or any GPS device uses, it's above you. So it has, let's say, poor elevation estimation because all satellites are at a similar range to you. But when it comes to the determination of the actual location on Earth, that's actually easier to do. So the way to overcome this problem is to measure the coordinates in Google Earth. I found that Google Earth can be quite accurate, and it has a good elevation model. So let me show you one example of a camera that is in one town in Croatia, and I can show you how we accurately measured its location. So we know that the camera is on a window that's basically right here and above this window. So what you can do is you can take this, make a
Dennis,
little
I can't
marker.
see anything.
Oh, sorry, of course, forgot to share my screen. Thank you very much. Okay, there we go. So now you can see it. We have, we zoom in as much as we can in Google Earth to the exact location of the camera, not the location of your house, the camera. And then you take your little marker and then you move it around until you get it as accurately as possible. Of course, I already have a marker here, right? So let me show you this other window that pops up when you have it, and then you can see how the coordinates are changing. And then you get that as accurate as possible. And you can just copy these coordinates directly into the config file, the latitude and the longitude. And as for the elevation, well, you can read the elevation right here in Google Earth. And also, usually this elevation is going to be off the neighboring terrain. So you might want to add a couple of meters to that to get the accurate location, the accurate elevation of the camera itself, right? And generally, that's about it. So I recommend an accuracy of at least 10 meters. These cameras have an astrometric accuracy of around, let's say, 1 arc minute, which translates to about, let's say, 30 meters to at a range of 100 kilometers. So if the location of your camera is wrong, if the error in the location is higher than 30 meters, then it's actually can be visible when we compute meteor trajectories, because all measurements will be offset by 30 meters, just because how accurate these cameras are. So we want to make sure that you get this location as accurately as possible. This is very, very important. Okay. Are there any questions at this point? Okay, I will take that as a no. And next thing we're going to do is we're going to discuss setting some things in the config file. So assuming that the location is accurate, let me just open an example config file here. So assuming that these coordinates are correct, the next thing that you should set is the field of view. So basically, you know which lens you mounted onto your sensor. Is it the 4mm lens? Is it the 6mm lens? Is it the 8mm lens? So what you want to do is set the approximate field of view here, which will help you to estimate the initial scale when we run SkyFit. So if you have the 4mm lens, the field of view is about 88 times 48 degrees. If you have the 6mm lens, the field of view is about 53 times 30. And if you have the 8mm lens, that's I'd say a bit of an issue, because some are designed for larger sensors and some for smaller, but it's usually around 40 times 20 degrees. So you might want to use those values. It's going to help you to get the estimate of the initial scale. So now that the config file has been set up, we can start fitting our plate. And for that, I'm going to use one camera in the UK. And the reason is simple. I'm going to use it because it has a lot of stuff in the field of view. For example, there's a tree and there are many other things. So I just want to show you how to accurately and properly create a mask for it. Because it's very important to mask out all objects that are inside the field of view. So for example, you can see there's a piece of roof. There's a roof, there's a chimney, a tree, another tree here. So what we want to do here is completely block everything out because the star detector and the meteor detector will get confused and they will either get a lot of false positives or they will not work at all. The star detector is some sort of a primitive edge detector. So it tends to detect a lot of stuff at the edges right here. And then you're just going to get, and you're going to detect too many stars and they're just going to say, oh, you know, something's wrong. I can't detect any stars. There's a problem. To solve that. So it's very important to have a good mask. The way I like to do that is by taking an image. I use the bin viewer software and I save one image as a BMP. Or if the star detection works at all, I like to use this flat here because this flat removes the background, but you still have things that are static. So if you have this file and you need a mask, you can just use this flat and rename it. Copy, rename, and then block everything out. So I'm going to remove the mask that I currently have. It's right here. It's called mask.bmp. I'm going to remove that. I'm going to take this flat. I'm going to copy, paste, and I have a copy here. And I'm going to change the name to mask. So I have this mask BMP, and it looks exactly like the flat. And I just have to select this stuff and remove that stuff. And for that, I'm going to use GIMP. You have that installed in your Pis. This program exists for Windows, Linux, any operating system. I think it's really easy to use. So now that I open this in GIMP, I use this lasso tool or the free select tool, and I kind of leave very liberal boundaries between the actual objects and the sky. And especially if there's a tree involved, they tend to sway in the wind. So you want to make sure you kind of cover the potential range of the swaying. So the way I do it is I would just simply do it like this. And then if there's a chimney here, you might want to kind of block that part off too. If there's some smoke coming out of it, that might cause some issues during detection. And then you go all the way down here. And if you see the horizon, you can actually just take a chunk out of the horizon because usually there you can't really see much. And then make sure to, you know, block off the tree. And then this tree is closer, so it might sway a bit more. So I want to make sure I leave some room for it. Make sure to get everything like this. And I go back and I just connect to this part. I press enter to save this selection. And then I press delete on my keyboard and it removes this part where the sky is. And the next thing I want to do is I want to block off the parts that I masked out. So I can go do select and invert. And this will invert the selection. So the middle part is no longer going to be selected, but the edges are. And then I press delete again to delete those edges. And what I have to do now is I need to paint them black. So make sure that the color here is black. All these numbers are set to 0. And I select the paint bucket tool. And you can actually make sure this option is turned on. It says fill hole selection. And I can just press here and it's just going to select every part that we want to block out. And we can save this. File, overwrite mask.bmp. And that's how we get a good mask. I think this is the easiest way, the most reliable way. And of course, once you're done, you need to transfer this to the Pi, or make sure if you already are on the Pi that it's in the right directory, and it needs to be in the source RMS directory, right? That's where it's going to read the mask from. And if it asks you this, it's fine. Discard changes. We already saved it, and there it is. Here's my mask file. Okay, so now that the mask is fine, the config file is fine, we can actually start making the plate. And to do that, I'm going to use my RMS installation. I'm currently on Linux, but this should work on Windows as well. And what I need to do is I need to navigate to this folder here. The easiest way to do that, I mean, you can do it by hand, but what I like to do is just copy the whole address of the directory. And then inside my source RMS directory with all the libraries installed, I just do Python -m utils.skyfit2. And it's very important that the capital letters are set properly. So there's capital U, capital S, and capital F. And after that, I just paste the path to this directory that I want to use for SkyFit. And the last important part is to tell it to use the config file that is inside this directory. So as you might know, RMS has a default config file that is inside source RMS, and it will use it for everything unless you tell it that there's another config file it should be looking for in the destination directory. And the way you can tell it that is by doing --config dot. So this will tell it to look for a config file inside this directory you gave it. Okay, so if you're doing this on the Pi, there shouldn't be any issues. But the problem right now is that the Pi doesn't have the full library installation for SkyFit2. So you will have to do this on either a Linux machine or a Windows machine. Okay, but in the future iterations of SD card images, I will install everything. So you should be able to run this on the Pi as well. Okay, so we can run this command. And the first thing it's going to ask us is, do you have a plate par file? A plate par is just short for plate parameters, and plate is like an astrometric plate. It's basically a file with the transformations between the image and the sky and the other way around. So initially, if you're starting out, you do not have a plate par file. You're still trying to make a calibration. And if you don't have it, you have nothing to select. In this particular case, I do have a file, but I'm going to pretend that I don't have it. So I'm just going to press cancel. I say, I don't have this file. I'm going to make a plate par from scratch. And then if you don't have it, it asks you, okay, so what is the rough pointing? The easiest way to measure rough pointing is to actually, go outside and look where your camera's pointing at. You should know the rough azimuth and elevation of your camera pointing. In this particular case, I think it's around, let's say, it's pointing south. So azimuth is 180 and altitude maybe around 45 degrees. And I press OK, and SkyFit2 opens, and I can enlarge this. And I can see that the stars don't really match. I don't really see a big match here. What you could do is you could kind of move it around and try to find the match, try to match up the coordinates. And the way you can do that is quite easy. Use WASD keys on your keyboard. So if you ever played a video game, those are usually the keys you use to move around. So press W, stars goes up. If I press S, stars go down. A and D, they make it move left or right. Or basically they're increasing and decreasing the azimuth. So you can see the azimuth up here as I'm pressing A and D keys, and you can see the altitude here as I'm pressing W and S, right? What you also want to make sure is before you start doing your astrometric fit is to find a good image. So what I recommend is you scroll through all the images that you have, all the FF files that are in the directory, and find one that looks best. And you can do that by pressing arrow keys left and right. So here I'm just going to press my right arrow key, and I just keep going right. And I see, all of these images are actually quite nice. I don't see any clouds. I don't see any fog. I don't see any mist. I don't see any issues. So I can basically use any of these. But if you're making your own, make sure that the image you use is the best image that you have available. No clouds, no mist, no issues, no problems. You want to make sure to have also a lot of stars that stretch all the way to the edges, not just in one part of the image or the middle part of the image. It's very important when we make the astrometric calibration that you have stars everywhere, okay? And the next thing you can do is you can stretch the levels, the image levels, to make this image look nicer. And you can see here at the right side of the user interface, we have several tabs. And the first tab is levels. So you can actually close these and open. And what image levels are is you can just adjust the white point and the black point. It basically means, how bright is the brightest pixel on the image and how dark is the darkest pixel on the image. And what you have here is this little histogram. And what you usually want is you want to adjust the white point and the black point to be kind of at the edges of this histogram. So we did this manually. We also have an automatic option. The automatic option turns on when you press Control A like alpha. So I can do Control A, and you can see the levels automatically adjusted, and I can turn it off by pressing Control A again. You can see there's only a slight difference because the automatic way is as good as the manual way most of the times, right? Okay, so now that this is nice, I can see that there are a lot of stars, and I can start doing my astrometric fit. We still have a problem though. We don't have a rough match to the catalog stars and the image stars. So the catalog stars here are represented with these red circles, and I can't really see any of them matching up well to the image stars. You can do this manually, as I said before. You can just kind of move stuff around and try to get it to match and everything. That's one valid way of doing it. Or we have a nice piece of code that when you press Control X, what's going to happen is it's going to take this whole image and upload it to astrometry.net. And if you look at the terminal, it's going to tell you what's going on. It says uploading the whole image to astrometry.net. Astrometry.net is an internet service where you can upload your image, and it's going to find the stars on the image, and it's going to provide a rough solution to your for your image. And it's going to tell you just a very rough mapping between your between the image and the sky. Now, this takes a while and doesn't succeed 100% of the times you're trying to do this, but it works in most cases, especially if you have a narrow field of view and you can't really find where the pointing is. It can be quite challenging. So this is the best way to do it. And you just press Control X and you wait for a minute or two, and usually finds a solution. And what it's going to do then, it's going to show us where it thinks the pointing is. Now, there's one issue with astrometry.net is that I haven't been able to figure out exactly what is the rotation that it reports back. It just gives us some sort of an orientation that I haven't been able to transform into I would say, understanding of the orientation in SkyFit. But what you can do is you can adjust the rotation manually using the keys Q and E. So if you look down the keyboard, you will see that Q and E are close to WASD, right? So you can use that for, oh, there we go. In this particular case, it failed to find a solution. Now, what you can do is astrometry.net procedure will provide you with the link. And sometimes it will report a failure because it just runs out of time of how many, like the software constantly keeps querying, like, did you solve the image? No. Did you solve the image? No. At one time, the software is like, okay, you didn't solve the image. But it provides you the link so you can actually go to the website and check what the status is. So you can take this link, copy it, and then paste it into your browser. And let me just open mine out here, and then I'm gonna paste it here, and it says it's still processing. So job status is processing. It still is not solved. So what you could do is you could wait until this gets solved, and then go back and try to find the exact location where it is on the image. So you can see it's actually still waiting for the processing to start. Looks like astrometry.net is busy now. But most of the cases, we don't need astrometry.net to work. What we can do is we can try to adjust this manually. I know, for example, that it should be around 170 or something like that. And try to do this manually. Let me just try to find the correct. Is the scale fine? Yeah, I think the scale is fine. And the way we can do this is we can shift the image around, and then we can check how the image stars move and how the catalog stars move. And that's a really good indication that if you have a good pointing or not. So in this particular case, what you can do is you can tell that if I move the image stars, that they're actually rotating. Okay, I think we have it all wrong. This here is Polaris. As you can obviously see that all stars are moving, but this one is not. So what I need to do is I need to change my pointing. I'm going to press V for victory, and say that the azimuth is around, let's say, 20 degrees, and altitude is around 45. Okay, and this grid is by right ascension and declination, and we can actually adjust this to be close to Polaris, and there we go. We have our match. You can see these stars are close by, and we can start our fitting now. And once you have this rough match, what you do is you turn on the star picking mode. And I understand there are a lot of keyboard shortcuts, but to help you with that, there's a little hotkey list here, and you can read that to figure out what every key does. I think that's quite helpful. So to begin the star picking, you do Control R, like radio. And then a big feature of SkyFit2 that did not exist in SkyFit1 is that you can zoom in. So you can just scroll your mouse and just zoom in onto the star that you want to pick. And once you identify which stars are pairs, you just click on the image star, and a blue X will appear on the closest catalog star to it. And most of the cases, this catalog star will actually match the image star, but if it doesn't, you can change which one it is. For example, if it's this one here, you can see that the blue X moved, or in this case, I'm just gonna switch it back. Once you're happy with your choice, you press enter on your keyboard, and that's it. The pairing has been made. So I can zoom out and choose another star, for example, this one here. Now, one thing that you can adjust now is the size of this annulus. So as you can see, I can make it bigger or smaller. And to do that, I just hold the control key on my keyboard, and it just gets bigger or smaller. And the correct size is such that it completely encompasses the star that you're trying to pick. And this will be used later to measure the brightness of the star. So I'd say this size is fine. I click on this star, the blue X appeared here, this is the right pair, and I press X. And now we have 2 pairs. We need to get at least 5 to estimate the rough pointing. Okay, so let's do a few more. I like this one here, for example, looks good. Pressing enter. The choice of your stars should be, you need to make sure the star is bright enough. Choose something that has a nice signal to noise ratio. It's not too faint. For example, if I was choosing stars, I would maybe avoid, like, let's say this star here. I don't think it's a good choice. And then I can go here, for example, add this one, and maybe, let's say this one here. Okay, now we have enough stars for a rough pointing match. What we can do now is we can refit the pointing to make our picking easier. And to do that, we can open this Fit Parameters tab on the side, where we have a lot of different options. But for now, we're just going to press this Fit option. And you can see that the stars moved, the pointing moved, and now the fit looks a bit better. And what we also see are these long lines. And these long lines indicate what is the fit error, the error between the observed and the computed positions of stars, times 100. So you can see here, for example, the error seems to be, let's say, 10 or so pixels, or maybe even more, but and the error here is much larger. Just to show you that there's, an error. Now, what does it mean that there's an error? Which it just means that we only picked 5 stars and we still didn't fit the full distortion model. So when you start it, you will get large errors. And then as you add more stars, the error will go down because we can actually fit the distortion. And one thing that I did now is I right-clicked on the image, and this removed a star. So in case you make a bad pair, for example, if I don't like this star, I can just right-click on this, and it's going to disappear. But I actually liked it initially, so I'm just going to add it again. And I'm just going to add a few more stars here, so we can proceed to the next step. So as I said, try to pick bright stars, because bright stars can have a nice signal to noise ratio, so we can estimate their accurate position really well. Okay, so the next thing we have to talk about is, how do we choose a correct distortion model? Previously, until a couple of months ago, in our GMN tools, we only had one distortion model, which here is called the Poly 3 Plus Radial. What this model does, it basically says, okay, I need to estimate this distortion somehow. And what we did is we applied a third order polynomial between the coordinates on the sky and the coordinates on the image. Now, that is fine, but the problem is that if you have this complicated mustache distortion, that model might not be enough. But it works for any type of weird distortions. For example, if you have a lens looking through a dome and the dome is introducing some weird problems, it's going to work better than other types of distortions. But very recently, we developed a new radial method, which basically says, okay, I'm not going to stretch the whole image with a polynomial up or down. What I'm going to do is I'm just going to find the center of projection on the image, and I'm just going to radially stretch the image out or in from that center. And it turns out that method works better than the polynomial method. About, let's say, at least 50% to about 2 times better than the previous method, depending on the lens and the setup. So the way to switch to this method is here in this distortion model. You can choose these different radial methods now. And when you start fitting your plate, I recommend you start with the radial 3 odd method. And this is really cool because it uses a very simple model that can be fit on any lenses with a small number of stars. So the way things work is that if you have a more complicated model with more parameters, more complexity, more of the curves that you can fit, you need more stars. Otherwise, you can fit whatever you want, and that's not good. This model is really cool because it has only one radial parameter, which is basically telling it that the how the radius is moving. Now, this is fine for initial fit, but later we'll add a 5th order and 7th order. Currently, we have this radial 3, which means we only have 1/3 order radial polynomial. It sounds complicated, but don't worry about it. Just make sure to understand the procedure. So now that we've chosen radial 3 odd, we can press fit. And then suddenly, oh, look at that. Our fit is much better. Look at these stars here. They fit 10 times better than before, especially these stars at the edges. So we can zoom in now. You can click here and select this star. You can see that it's a much better fit. And for example, I like this star here. I'm going to add it now. This star here. I'm going to add this one. Maybe this one here. And as you can see that I'm changing the size of the annulus. Again, I hold control and then I scroll to change the size to fit every star. And then I'm going to do this one. Let's see, this one here is also nice. I just want to add a good number. Okay, and now I see these this hotkey list is in my way, but I can hide it by pressing F1. It actually says here, F1 hide show this text. So I'm going to press F1. I want to make it disappear, and there we go. So I get good access to these stars here. They're not hidden anymore. And I'm just going to add this star here too. Okay, now that we have more stars, we can fit again. We press fit, and there we go. We have a model, but you can see that we're starting to have these large errors at the edges. And when I said that the current model that we're using is nice, it's because it's simple, but it's not complex enough to fully model the distortion of this lens. And you can see that all errors that you're getting are kind of radiating away from the center. And that's simple because our radial model is not complex enough. There's a simple way to fix that. We just do radial 5. And now we have one extra parameter that's being fitted. And now we press fit, and the fit is much better. You can see all these error lines, the little tails are much smaller. And we can actually see a graph of errors if we press this astrometry button here. It's going to open a new window, and this new window is going to show us what the distribution of the errors are. So here you can see this is the radius from the center in degrees on the sky versus the radius error in arc minutes. And what you want to see is kind of a random scatter around 0. You don't want to see any weird trends and any weird curves and lines. So let me close this and switch back to the radial 3 model. And I'm going to do the fit again to get these large errors. And then let's look at the graph now. There you go. You can see that there's this kind of weird curve. They're all not randomly scattered around 0. And this is a simple indication that's telling you, okay, I need to increase the complexity of my model. It's not, taking these weird curves into account. I just need to bump it up. Okay, so let's go back to radial 5 and let's do our fit. And again, this looks much better. To get really good fit, what you have to do with radial models in particular is to make sure that you cover the whole range of radii from the center of the image, right? So if we look at this astrometry error graph, we can see that we're actually doing a good job. Maybe we should try to get a few stars here close to the center of the image, and maybe add a few more stars here at the edges, just to make sure that our model is nice and correct. Okay, so I'm just gonna, for example, add this star here. add this star here. And, you know, I want to avoid these are faint stars. If I centroid this, it's, you know, it can be anywhere. So I want to avoid that part and make sure the stars that I'm using are nice and bright. And this one here, I would say is reasonably good. And this one here, just add a few more. And at the edges, I kind of, you know, I want to make sure to include as many stars as possible, even though they're not as bright. And here you can see that we have a binary star. So if I zoom in, you can see 2 catalog stars. You want to avoid those because you don't really know which one you're picking, and that can be hard. So I'm just going to zoom out and go back in here and pick this one here. Okay, and let's make another fit. Okay, now you can see we're getting kind of some larger errors here. We might want to increase the complexity of our model, but let's just pick a few more. Just make sure we have, no, we have a lot of stars. Do another fit. Look at this astrometry, and there we go. The more stars we added, we're just starting to see that again, we seem to have some sort of a curve. Something's going on here. We need to add more complexity to our model. And there is one option that I didn't turn on, and you should always keep turned on, and that is a symmetry correction. So what happens is that most of the times when you mount your lens onto your camera board, that lens is not mounted perfectly perpendicular to the image sensor. There's a tiny bit offset. It's either left or right. And you can actually see this effect here. So the way to correct this is by turning on a symmetry correction. And this will introduce a few more extra parameters in the model that's going to try to correct for that. And I can press fit now, and that should help with the asymmetry correction. And I can press fit a few more times, and let's see if we have any improvement. No, we actually still have this curve here, which means that we have to go to radial 7. And
you may try to add those stars in upper left corner, because that
yeah,
may
you're right. So they don't seem to be fitting well here. And I'm going to add a few more here. So that's a general check to make at the end, to make sure that you kind of covered the whole field of view and you don't get any big offsets anywhere. So, you know, what would happen if I just fit stars in the right side of the image? Well, the stars in the left side of the image are not going to look good, right? So that is.
What about picking some stars down at the bottom of the image? There seem to be some bright ones there.
Yep, that's a good idea. We can add a few more here. So good wide coverage is very important if we want to get a good fit. There we go. Okay, let's try fitting this again. And okay, we have a reasonably good fit. And let's press this astrometry button. And you can see we have some sort of a scatter at the ends here. Once you see that, I would recommend you go back and inspect if your centroids are good. In this case, I think they actually are. All of the ones that we did here, for example, they look actually quite good. So we might want to go and do the final 9th order polynomial and see if that's going to polish out the errors that we're getting. And no, it just seems that at the ends here, we have some larger errors than we'd want. Let's just try repicking these stars. I think we're not going to achieve much, but you never know. See with these faint ones, it's kind of hard to tell where they are exactly. But I think that's generally going to be fine. Okay, and this is the best we can get at the moment. We have a few stars. They don't fit incredibly well. One other strategy that you can try is try to pick other stars around the ones with large errors and see if they fit well. If they fit well, this means that this one star in particular has some sort of an issue, has some sort of a problem, and we can remove it. So in this case, I'm gonna just remove this star here with this large error and refit everything and see if we get an improvement. I think we did get something better. So if we look at the astrometry fit errors now, they all look quite decent, all within, say, 2 arc minutes. And if we look generally at our fit errors, we get a fit error of about 0.83 arc minutes, which is really, really good and accurate. So before, if we used different methods, we would get probably an error of around 1.5 arc minutes. And we can try that, actually. We can switch to the old poly 3 plus radial method and do the fit with that and see what we get. See if we get a better fit or a worse fit. Okay, that's the first iteration, which usually needs some improvement. So we can just hit the fit button several times, and then the fit is going to converge and it's going to become better with more iterations. There we go. We ran the fit several times, and you can obviously see immediately that the fit is not as good as before. So you can see we have this trend here. The average fit error is 1.82 arc minutes. So that's almost more than 2 times higher than what we had with the radial method, right? So what we need to do here definitely is switch back to this radial method and hit fit for just a couple of times for the solution to, converge, and we're good here in terms of astrometry. Okay, so let us look at the graph again. Yeah, this looks really good. And if we look at the final number, there we go. Here we are at the end. And we are basically done with the astrometric calibration. So this might have looked complicated and, involved a lot of steps. But if you're doing this operationally, you don't really need to go through all of these steps step by step and very little, granular, start from the 3rd order, increase to the 5th, blah, 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 blah. The easiest way you can do it, and the way I do it, is when I open up SkyFit, I just make sure that all these 3 are selected. I have refraction on, equal aspect on, and a symmetry correction on. What do these mean? Well, refraction is trying to compensate for the atmospheric refraction of the stars. So at low elevations, starlight has to go through a lot of atmosphere, and it actually bends the light up. So that's why, for example, we see the sun longer. The sun actually sets, but it refracts through the atmosphere, and we actually see it when it's that kind of low on the horizon. And it's all caused by refraction. So when you turn this on, it's used to compensate for this offset. And we can get much better fits if this is on. So keep this on. Equal aspect. Our modern digital IMX291 and other cameras have an equal image aspect. What that means is that the pixels are square. And basically any movement in X, Y direction or anywhere, it's going to translate to the same, say, amount on the sky. But some older cameras, like all analog cameras, they didn't have square pixels. Some had like an aspect ratio where when one part of the image was squished or stretched. And there's another extra parameter that gets fit when this equal aspect is turned off. But for these cameras, we know that we have an equal aspect. So we keep this on, refraction on, equal aspect on. And finally, this is symmetry correction, which is if the lens is not properly seated, or even if it is properly seated, the movement and the offset can be so tiny but still make a significant influence on the quality of the fit. So turn SkyFit on, you turn refraction, equal aspect, asymmetry on, and I usually switch to radial 5 as my initial fit. And then I do my picking, I do my alignment, I do the fits, and if I have to go higher, I do radial 7 or radial 9. And after that is done. I'm just gonna switch back to radial 9. After that is done, we've finished the astrometry part. So basically the transformation between image and sky coordinates and back. And what we can do is we can hit Control S to save the plate power file onto the disk. And when I do that in the terminal, it's going to say saved state to file, plate power file written to blah, 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 blah. Okay. And before we proceed to the photometric calibration, are there any questions at this point?
Yeah, I have a question, Dennis.
Yeah, go ahead.
When you switch to the new method, the radial 3, 4, 5, 7 method, can you still make cal files for CAMs?
Yeah, that's a good question. So we have to talk to Pete Grell about this. I think he needs to implement these. Well, actually did make an implementation of these methods, but I'm not sure if he has that in, I think it's the coincidence software or whatever that actually reads the cal files. So you need to talk to him, make sure that everything is implemented on his end, and then we can make a cal file with this particular type of distortion.
Yeah, because currently in the cal files is exactly the poly 3 plus radial, right?
Yep. Yeah. So right now, right now that's the case. So if you want to use cams, until Pete makes the implementation and a switchover, it needs to be a poly 3 radial method, right? It's not as good, but it's gonna still work okay.
I want to say something about the cams. Everything, as far as I know, everything we need for positional data is in the detect info file. And in coincidence, in the further pipeline of cams, coincidence only looks in the cal file for the photometric parameters, not for anything else. So in fact, we can use a dummy cal file. If these photometric parameters are inside, coincidence is habit. But the positional data, that's completely in the detect info file, as far as I know.
Thanks.
Dennis, I have a question for you. It's Claude from Quebec.
Mm-hmm.
I just wanted to know how frequent do you have to remake your plate bar or SkyFit?
Mm-hmm. Yeah, that's a good question. So actually, once you make an initial calibration plate with the radial method mostly, and if nothing changes in terms of the hardware, if you didn't change the lens, if you didn't kind of move the lens with respect to the sensor or anything, it should be good for a while because the pointing gets recalibrated every night. But in terms of the distortion, it should not be changing significantly, as far as I know. Now, there might be some thermal effects and the distortion might change, and we will probably look into this in the future. But right now, it should be good. Once you make one, you're good.
Okay. I've noticed the reports in the morning that sometimes the astrometric report is very accurate, and some other times it's less accurate. Well, why is this?
It could be also on the number of stars it's used and how accurately you can estimate the location of the stars. But usually, if you have kind of high quality data, there shouldn't be any issues. And also depends on the quality of the astrometric plate.
Okay, thank you very much.
Yep. It's all, so that's the reason why we avoid using meteors detected through clouds. You really need a lot of stars to make a good calibration and high quality measurements. If it's fuzzy and you can't really see them, then we can't. The quality is going to be bad, right? That's why we kind of avoid using meteors detected through clouds. You just don't know. So probably one more thing to show you with the astrometric calibration now that we did this I'm just gonna turn the star picking mode off. I'm gonna go back here. So one thing to note in SkyFit is that every time you press any of these buttons and you want to go back and press any of the hotkeys, you have to press escape. You see it says right here, press escape to focus on the image. Because the way we do key detection, it's only in this main image part. Okay, but never mind. So what I'm gonna do now is I'm gonna turn off the image picking mode. I'm gonna do Control R, and you can see this little cursor is gonna disappear. And then I'm gonna start moving the switching through the image, and now you can see, there we go, dawn is here. And then as you can see, as we go through the night, the astrometry shifts. So as you can see, all the stars are shifted a bit. All the image stars and the calibration stars are no longer in the center. Especially you can see it nicely here, right? There's an offset. And again, it's simply because of thermal effects. The camera pointing is drifting, and what you want to do is, and what RMS does is automatically recalibrates this pointing. But there's an option in SkyFit to just recalibrate the pointing without recalibrating any of the radial parameters. So if any of the distortion parameters. So basically the difference is that if you want to fit the distortion, you have to make sure you have good coverage, the stars are picked everywhere. But if you want to just refit the pointing, you can use as little as, let's say, 8 stars and make a fit on that. And there's a special option to do that. So let me just show you. I'm just going to pick a few stars. Again, bright stars with nice signal to noise. And example here, I don't really need to go. No, I think this is the problem star. This one here is much better. Okay, so I have only, let's say, less than 10. And if I want to just refit the pointing, there's a special button here. It says only fit pointing. I turn this on and press fit, and there we go. It just ever so slightly moved the stars and the fits. But if we look across the field of view, we can see that the stars are match. The stars match again to where they should be in the image. You can see it there. So before they were somewhere here, and now they're right here. So that's just an extra feature that if you already have a distortion, but you're doing something special with this one image, you can just do this only pointing fitting. But make sure if you're fitting the distortion that this is turned off. Otherwise, the distortion will not be fit. Okay. And now this is it in terms of the astrometry. The next step is to do the photometric calibration. Photometric calibration is simply how do we convert these image intensities into magnitudes. That's what the photometric calibration is doing, right? Because that way we can actually measure the magnitudes of meteors. Now, because I closed the previous window and deselected the old stars, I don't have them selected anymore. But when we saved the plate part to disk, it also saved what's called a state file. A state file, it just basically grabs the state of SkyFit as it is at the time of saving, and then you can just load everything back up. And you can actually see it in this directory that we're working in. There's a little SkyFit state file. There we go, right here. It's called SkyFit latest state. And then what I can do is I can just reload whatever I had before by directly opening this file here. So I'm calling my command again, SkyFit blah, blah, blah. And I am back in here and I just say SkyFit state file and I do enter and I'm just gonna open what we had before. These stars that we had. And then what we can do is we don't have to reselect anything. We can just look at the photometry that we had before. Now, the photometry calibration is actually automatically recalibrated with the astrometric calibration. And the only thing that you basically need to get right in terms of the photometry is the vignetting coefficient. What is vignetting? So basically the sensitivity drops off as you move away from the center of the field of view. You might have seen it in old cameras that the edges are kind of dark and murky and the center is bright. And you can also see that on like flats, right? That's why if you ever did astrophotography, you need to take flat frames and then divide the data with the flats and kind of to correct all of that. Here, we're using it with the simple vignetting coefficient. And usually SkyFit estimates the vignetting coefficient by itself, but it's kind of very dependent on if you can get the photometry of the stars at the edges right. So sometimes it messes up. So what I like to do is I just like to set this vignetting coefficient manually, and we know exactly what the vignetting coefficient is for the 4 and 6 and 8 millimeter lenses. It's about 0.01 radians per pixel. It's just the number that goes into a little equation that corrects the vignetting. And the way I like to do that is I just close everything and I open the plate part file directly. I found it here, and I open it in a text editor. And as you can see, a plate part file is nothing but a list of these parameters that are used for fitting. And here I'm going to find the vignetting coefficient. There we go. And set it manually to 0.001 and save. And that's basically everything you need to do in terms of photometry. RMS will automatically recalibrate everything that you have. You don't even need to spend a lot of time making sure you have accurate photometry, blah, 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 blah. No, you just set the vignetting coefficient to 0.001 and that's it. You're basically done. And what happens later on is that RMS will recalibrate the astrometry. So if we look at the astrometry report that was generated for the station before, it'll redo the pointing, and it will also redo the photometry. So here you can see how the pointing drifted throughout the night. This is the angular distance in arc minutes, and sometimes you can notice drifts are of up to 10 arc minutes, which when you contrast that to a precision that is below an arc minute, it makes a huge difference. But at the same time, RMS is also recalibrating the photometry. So this is the automated photometry report. And if you look, I've set the vignetting coefficient before is 0.001. And what does the vignetting coefficient does? So for example, if you look at the red dots here, you can see that they follow this vignetting coefficient, this vignetting model, right? So basically at the edges, if we did no correction whatsoever, the magnitude error would be about 1. So the stars at the edges are about 1 magnitude fainter than the stars in the middle, just because of vignetting. But when we make this correction, these blue points is the photometric fit after the vignetting correction. And it can be quite accurate, about 0.1, 0.2 magnitudes. This is the fit error, which is great. And also the important thing to say is that the photometry can vary throughout the night. You get moon, you get clouds, you get different, let's say, sky transparency changes, blah, blah, blah. And the photometry calibration also drifts throughout the night. And you can actually nicely see how that this makes a nice or a big impact in certain regions and not the others. For example, we have a camera which is high on a mountain in La Palma, and the way the photometric offset, or this photometric graph looks there, is just goes up, and it's just basically a straight line. The sky is perfect all night, and then as you get dawn, the sun goes up, the sky brightness changes, and the photometric offset just goes sharply down, and then the recording stops. But if you are in an urban environment, if you're in an environment that gets a cloud or different weather conditions, the photometry calibration will change. And here you don't really have to do anything. It just completely automatically recalibrate there for you. As long as the knitting coefficient is set correctly, there's nothing for you to do here. Okay, so we're done with the calibration part, and I'd like to proceed now to the manual reduction part. So just like in the previous tutorials, we had the SkyFit tutorial, which talks about how to make a calibration plate, and then a second tutorial which talks about how to, we have an interesting event, interesting fireball, how can you compute the trajectory manually, how can you do the analysis, blah, blah, blah. So before we get on to that, do you have any questions about anything we did previously? I see we have a couple of questions, here in the chat. If it's okay, I can start addressing these questions. Tamiyan, is there a table with these magic numbers somewhere? Sorry, what kind of magic numbers are you referring to?
Yeah, sorry, those were the magic numbers of the lens opening, the field of view.
Oh yeah, field of view. I think we have them somewhere up on GitHub or somewhere, or maybe in the parts list. But yeah, that's a good point. I think that's something we should add to the wiki, just so there's a list of that. Okay.
I recently fitted this this new lens here. Here it is. And to get astrometry.net working, I didn't have the field of view. So I hacked those out of the Astrometry net code. So it found the field of view for me. But, yeah.
That's great. One thing that I want to say is that remember that astrometry.net link that I opened? It took a long time to solve that image. I don't know why, but it actually did find a solution. You can see it here. So you can actually, we could use this right ascension and declination that we found in SkyFit if you were willing to wait for 10 or 15 minutes or however long it took to solve it. So again, if the astrometry.net, you don't get an initial solution, you just use the link and wait in your browser if you're too lazy to find the actual fit manually or whatever. It usually works. Okay. And as for the cal files, I can see that if the focus is too good, could that affect fitting with FWHM? We should, that's a good question. So sometimes, these days, I guess, lenses are so good that you can focus too well. And a star can look like, it can be like a pixel. And that is not good. The reason is simple. So when we centroid a star, which is basically just kind of computing the kind of brightness weighted center, you use the kind of the information from all the pixels around it to get a location of the star that is more precise than 1 pixel. You can, as you've seen during our fitting procedure, you get an accuracy that's like 0.2 pixels. The 0.2 pixels is only achievable if your star doesn't look like a single pixel. If your star is just this one little bright pixel, then you can't really tell, if it's better or more accurate than that. So I would say that the ideal full width at half maximum, that's what FWHM means, is about 3 pixels. It should be at least 3 pixels wide, kind of an average star in the field of view. So yes, focus can be too good. It's not good to have a perfect focus. You need to make sure the focus is good enough, but not too good. Okay, and finally, after calibration, you had results of 0.83 arc minutes. What is the ideal figures we need to aim for, and what figure is not accurate enough? So I'd say just look at the trends that you see in the fit residuals. If they're all scattered around 0 and you don't see any weird curves or anything, you achieved a good fit. So, and it also depends on the lens, right? So for example, you can achieve between, let's say, 0.5 and 1 arc minute precision with the 4 millimeter lens. You can achieve maybe half an arc minute with the 6 millimeter lens, and with the 8 millimeter lens, it can be even better. With the 16 millimeter, of course, you can achieve an accuracy of, like 10 arc seconds, even better than that. And on the other end, you know, with the alt sky, you're happy if you get, let's say, 5 arc minutes precision. It really depends on the lens you're using, right? But I'd say for the 4mm lens, at least 1 arc minute accuracy. That is what is expected. Okay, and oh yeah, there we go. The PDF gives the approximate field of view. Okay, do we have any other questions, suggestions? Well, if not, then the second part of this tutorial is going to be how to manually reduce some fireball data, which I think is very exciting. And here we're going to talk about one fireball that produced a meteorite, which ended up in the Adriatic Sea. So, you know, if you want to snorkel and try to do some underwater meteorite hunting, this will inform you where the meteorite ended up. But that's, I think, quite difficult. So once you have a meteorite fall or any bright fireball recorded with the RMS cameras, you will probably have this FR file. So what is the difference between an FF and an FR file? So let's look. What I'm going to do is I'm going to open these FF files in our bin viewer software. I'm just going to quickly open bin viewer to see this data. So this fireball was recorded from 2 stations. Both these stations were in Croatia, and the fireball was very close to Italy. So there we go. We have the images here. Here we have some bugs or birds and whatnot, and the fireball is right here. Very bright, very exciting, came down almost down to horizon. And when you have an FF file, that's great. But the issue is that it doesn't work that great for fireballs. Let me show you why. So if we go back to this bug that we have here, we can see that it's moving very fast across the field of view, and we can kind of even see the little wings flapping left and right. So if we were to reconstruct individual video frames from this, you can switch bin viewer to the frame mode, and you can kind of go step by step to the frames, and then you can see this kind of little line segments where the bug was, and that's basically per every video frame. And you can actually get a good estimate of the bug's location and position on every frame. Oh, there we go. It's coming back. There you go. So you can kind of nicely see where the bug was at every given time. But for fireballs, though, just because of the way the compression works, there's an issue, is that they look like what we call space invaders. So for example, look at this part here. And this is just simply because of the FTP compression that gets applied. It's used by RMS and CAMs just to reduce the data file size. That works great for fainter meteors, but for fireballs, because they're slow moving and very bright, you get these kinds of effects. To overcome this, we have a dedicated fireball detector that detects fireballs. And that data is saved as FR files. And we have an FR file here that we extracted from the folder, which had the original data set. And we can view these FR files by using the FR file viewer, which is in the RMS code base. And you can call it by Python -m utils FR bin viewer. And just paste the link to the folder, and okay, there we go. Of course, showing it on the wrong screen, but there we go. So you can see that we have raw video frames of the fireball here. And there we go. The fireball was tracked from this station, and we actually have the same thing from the other station, this station 02. And I'm just gonna open this here, and hopefully, there we go. So you can see it was recorded from the other station. and it was quite bright. And we had, I think, some fragmentation at the end, and that's it. Okay, this is another meteor here. So what we're going to do is we're going to load these files into SkyFit, make the calibration, improve the calibration, and then manually pick the positions on the fireball and compute the trajectory. First, we're going to start with this H camera. And again, as I did it before, I'm just going to open this in SkyFit, SkyFit2, paste it here, and of course, tell it I need to use a config file. This config file here, so it'll find it. And another option, we need to tell SkyFit that it needs to look for FR files. Usually it's just going to skip them, but there's a special option and that it's going to tell it to look for FR files. And we're going to do --FR here. And when we open SkyFit, we do have a plate par because I calibrated this station previously, and I will not be doing this again because now we know how to do the calibration yourself. I'm going to open it, and if I hide this, and if I go left and right, you can actually see this fireball here. And if you look at the name of the file that's open, it's FR blah, blah, blah. And you can nicely see the outline of the fireball, right? But now what you can do is you can switch to this manual reduction mode right here. There we go. And you will be able to pick individual locations on the fireball's trajectory. So now I'm using left and right keys to actually see the video frames of the fireball. There we go. You can see this very nicely here. And what we're going to do is we're going to pick these locations and compute the trajectory from that. Okay. Before we do that, though, there is an initial step that needs to be done. And I showed that before. Let's switch back to the SkyFit mode, adjust the levels a bit. And first, we have to realign the astrometric plate. So as I said before, you have a plate par and you have the distortion coefficients. But the problem is that sometimes it can move. The pointing moves, and then you just have to refit the pointing. And now you can do that very fast. Just select a couple of stars, a couple of bright stars here. I'd say about 10 or so at least, just to get a good feel for the pointing shift. I go here, it's even higher.
Some besides the fireball itself.
Yeah. Let's try to get some here. There's one here. And there we go. I'd say this is enough. And then we go to fit parameters and we do only fit pointing, and we're going to do refit. And it just shifted the location of the, just slightly shifted the location of the pointing, and that's it. I think the stars here fit quite well, and there's nothing much to do after that. Once that's done, just switch to manual reduction mode, and we can start picking the location of the fireball. You can do keys up and down to do like 10 frames forward and back. And the way to start, again, is to turn on this time the meteor picking mode, which is the same as the star picking mode. It's Control R. And again, you're going to get this nice little annulus here, and you should be able to start picking the location of the fireball. Now, this is the hard part. You need to find the first frame. There we go. It's right here. And then what you can do is you can press space to go to the next frame, and just press space again, and you're just going to keep going to the next frame. And what you have to do is on every single frame, you have to select and centroid the location of the fireball. That's basically it. And what you're going to do, what you're going to get is this kind of a helper line, which fits like a great circle onto the fireball's trajectory, which is kind of a line on a celestial sphere. and it's going to help you to know where the fireball is expected to be, because fireballs are supposed to be lines in 3D space, more or less. And you just keep going. You just keep selecting and adjusting the size and selecting the centroids of the fireball. And I'd say this initial part is quite easy. You can do it quite fast and accurately. The problem is once the fireball starts breaking up, it starts fragmenting, it becomes really bright. It's increasingly harder and harder to tell where the fireball is. Let me show you something. Let me skip 10 frames forward, So you're just looking at this and you're thinking, where's that one line? It's just this huge blob. So this is where this kind of turns from science into art. And what you want to do at this point is kind of shift the levels up to make sure you're just looking at the fireball and not other effects. But generally that's the approach you have to take. And we'll discuss about this in a few moments. Once it becomes brighter, it becomes increasingly harder and harder to tell where the centroid is. So what I usually do is I kind of try to estimate the size of the head of the fireball and not do the centroid on the, let's say, the whole thing, because the problem is you're trying to estimate where is the leading position of the main fragment. So what we're seeing here is the fireball started disintegrating in many little pieces. And here at the end, you have these kind of tiny little pieces that if you take a centroid of this, it's going to tell you, oh, the center of the fireball is here. But you're just kind of then focusing on those little tiny pieces that you don't care about. You only care about the largest, biggest piece, which is at the front. So what I usually do is just kind of try to estimate the location of that by matching the size of this inner circle of the annulus to the kind of the size of the fireball, and then you just kind of trying to make your guess. It is quite hard, subjective, and it's important to get it right. Otherwise, the speed of the fireball won't be good. There are several ways of doing it. I think this is the best that I've come up with, and sometimes you just have to kind of force it to a right position. In this particular case, what helps is that we kind of know the line it's supposed to be following from the initial observations that are not saturated, where the fireball is not this huge blob. And there you go. It's I don't know if I'm doing this right or not, but just go back a bit. When it gets hard, what I like to do is I like to go to the end. And there we go. And the fireball becomes small again. Here we don't have perfect tracking. So I'm just going to go backwards, try to get where the actual position of the fireball is, and figure out what's happening. So one thing to keep in mind is that the speed of the fireball doesn't change all that dramatically. So what you can do is you can kind of, like where is it now? It's somewhere here. Let's see if we can fit it here. And then there's another huge fragmentation. So if you see someone doing this automatically with like some sort of code or software, I would be very suspicious of what's going on, because this is so hard to do by hand that doing it in some sort of automated way is, I would say, almost impossible. Let's just take off. There we go. Some initial part here. Unless they can come up with some sort of a way to dynamically estimate the size and the fragmentation at the same moment, I would say it's all very, very, very hard. And now this is the part where we need to be careful. think I need to redo this a bit. Maybe it's even behind a bit. This part you will see during the trajectory estimation. This is going to be the trickiest part. The one with the highest errors, positional and velocity. Things are not going to look good here. But it really depends what we want. If you want the orbit of the fireball, the initial part is going to be just fine. Just exclude this part completely. And if you want the final position of where the meteorites fell, you just use this final part. That's it. And this part in the middle, I'd say it's only good in terms if you want to determine what happened during like the fragmentation process and stuff like that, which is also very important, and which basically what I've been mostly focusing on when I was analyzing the Winchcombe event, which most of the analysis, was done using SkyFit, believe it or not. So you guys have access to tools that you know, even the big professionals use, which I'm supposed to be one, I guess. And once we're done with this, I'm going to skip the same procedure from the other station because I already did that. And I will show you how to run the trajectory estimation. Oh, this is good. This part is going to be quite tricky. Yeah, I see I wasn't consistent between these two. I'll have to redo some of this stuff. Fortunately, Winchcombe was much easier because there I was able to use other data which wasn't as sensitive as our cameras. There we go. I think I redid this a bit better. I'm gonna call this done. The initial part is fine, and the last part is fine. And this part where the fireball is really bright is okay. You know, you would probably need to spend a couple of hours to get all of this right. But once you're happy with this, you just save, hit Control S, and it's going to save the plate part file that we recalibrated, but it's also going to save a couple of other files where the individual picks that we picked are stored, right? And then we can combine these measurements from this one station and the measurements from the other station to compute the trajectory. So we can very briefly look at the files that were saved. There's this one eCSV file that we can open. And it basically has all the information about the station, longitude, latitude, elevation, camera ID, blah, 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 and individual measurements. Basically the time of individual measurement, the right ascension, azimuth altitude on the sky, and even magnitude. But for fireballs, we can't use the magnitude because they're saturating. It's just all white. Any magnitude you estimate of a fireball using RMS data, the magnitude will be underestimated by a lot. So you cannot be doing any photometry here. It's just, it is not possible. Okay. So this is in a format that Jim Rowe is working on, and we're trying to get it adopted as some sort of an international standard. And once you have this from one station and the same thing from this other station, and you can see this eCSV file is right here, you can compute the trajectory. And to do that, we need to fire up our Western Meteor PyLib software and call the trajectory solver. And again, it's the same approach, but a different command, Python -m. You're going to call it wmpl.formats.ecsv because we're using the eCSV files as the input format. And then we're going to give it the path to where all the data folders are. And that's basically here in the SkyFit tutorial folder. and we will tell it to just go in and find all eCSV files. So we'll automatically locate this eCSV file from this station and this eCSV file from this other station. To do that, we call the command by doing --walk. It's going to walk down through all the directories and just going to find all these. And then we're going to tell it to, for now, disable the complex Monte Carlo procedure to compute the uncertainties. We don't need that right now. You just do -d and then do -x, which will not show the plots on the screen, but we're just going to save them to disk. And this is the basic command. And we run that. It's going to go in, find the files, and it's going to compute the trajectory solution. And it's going to take some time. There we go. It's working. Analyzing things, trying to figure out the timing differences. And after that, it's going to estimate, there we go, the initial velocity, the radiant. It's going to estimate the orbit, save that to disk. It's going to produce a couple of graphs, and that is essentially it. Okay, now it's done. And this is the folder here with the trajectory. I'm just going to show it like this. We can see that the modified time is basically, I think I want to go in. We're going to see the trajectory. The modified time is about now. And what we can then do is we can look at the map, and we can see where the stations were. And Italy is here, and it just fell just off of the coast here and end up in the sea. It did not reach land. You know, we can run some dark flight code, but it's definitely not there. The next thing we can do is we can look at the total fit residuals. So what this thing does is shows you how the when you're fitting the trajectory, it's going to show you how the trajectory is assumed to be a straight line. And if there's some sort of offset from the trajectory, you're going to see it here. And what we see for most meteorite dropping events is at the end, we see a large offset. It looks like the final fragment, in the final fragmentation, the fragments get some sort of transversal velocity component. It basically means the fireball is going straight, and then it fragments, and during the fragmentation, the pieces kind of fall, kind of go into different directions, and then it kind of gets a side, doesn't even follow the initial trajectory, but kind of goes to the side. And that's what we're seeing here. And we can very accurately determine, if we just take the final part of the trajectory, we can determine where that endpoint was to within better than 50 meters, no problem every time. We can then look at, for example, the velocity, how it changed, and we can see here, it started at like 17 kilometers a second, and then decelerated down to about 4 kilometers a second, which really indicates that we're talking about a meteorite fall, especially if the end height is below 30 kilometers. Here, I think it was like 27 or 8, and that we have, let's say, 10 to 100 grams on the ground. It really depends. More analysis needs to be done, but it ended up in the sea, so we don't care. Okay, and that's about it. Does anyone have any questions about this stuff?
Yes, Dennis. Is there any documentation for us to read? Because it was a nice lecture that you gave us, but to remember all of this.
Yep.
Okay.
Yeah, that's a good point. Currently, the only documentation is going to be this video. We have to work on writing some, and we didn't do that because a lot of this stuff was changing so fast that it made no sense to write anything, because the moment it was written, it was obsolete and not useful. So I think we're currently at the state where the tools are developed so much that there won't be any big changes. So we'll try to have some sort of documentation.
Okay. Well, the part that interests me the most is to see the fireballs, because I had a few fireballs on my cameras, and the only thing I saw was sparkles of light all over, and I couldn't see the center, the fireball like so. So that's probably the part that interests me the most. For if I can have them, well, if I have a fireball, I will be able to see it and show it to our visitors at the planetarium.
So you were saying that it was not visible or wasn't recorded?
Yes, it was recorded, but it was like on your video. It was like a splash, and the center we didn't see the center, the ball, the brightness of the center. We couldn't see it. We only saw like a flash of light, sparkles everywhere, but not the fireball.
It could be that we're looking at the FR file that has raw video frames.
No, but I've just learned about the FR files.
Okay. Yeah, because in
No.
them you will get the full video that doesn't suffer from any compression artifacts that the FF files usually have.
Okay.
Yeah.
But the FR files, they automatically make themselves when you have a fireball?
Yep. So every time, so the raw video frames are present in the memory of the Raspberry Pi for like 20 seconds. In those 20 seconds, the fireball detector goes in, determines there's a fireball, and saves the raw frames to disk. It actually doesn't save the whole frames, just saves the little cutouts to save space, right? And if it was not detected by the fireball detector, then it's not there.
It's not there. Okay. Well, for me it's new. Now I know that
Yeah.
there's something to look at.
Yeah, they should be there. So one thing that I can show you that maybe might be useful is that how to you can make a video or extract individual frames from an FR file. So let me just move the FR file into this folder here. And then there's a little command. We can do utils FR bin viewer. And then you give it -E for extract. And then, actually, I forgot to put the FF file in here.
And then again, you're not sharing.
Of course, I'm not.
Yeah, that would be nice.
There we go. So it's extracting these individual video frames, and the command that I ran was FR bin viewer. I gave it the path to the folder, and I said -E at the end. And what it's going to do is just going to save the individual reconstructed video frames.
Okay.
And that's not possible for a single FR file?
Yeah, so you can do that out of a single FR file. And to get the background, so the FR files only hold the cutouts, right? So if you don't have an FF file in the background, you will not get the background. You will get just the little cutouts here.
Oh, okay.
Yeah. So sometimes the fireball will be detected by the fireball detector, and you will only get the little cutouts, but will not get the background FF file. What you have to do in that case is you have to manually go in and save the FF file before it gets deleted. So the reason why we don't save the FF files for every FR files is because the fireball detector can sometimes trigger on birds, bats, other things, planes. And if we did that, there would be a lot of huge FF files everywhere. And that's why we were trying to avoid that as much as we can. Until we improve the fireball detector that it's, I'd say bulletproof, and then there shouldn't be any issues.
And where should I find the FR files?
They should be in the same folder as the FF files.
Ah, okay, good.
So once, let me see.
No, it's okay. It's just that I haven't noticed the FR files before.
Yeah, so there we go. You see, this is the archive directory that I opened, and the FF files are here, and the FR files are right here. They're just
Okay.
inside the same folder, right? Just below. And they can range in size from tiny to huge depending on how long the event was.
But they are binary files?
Yep, they're binary files and can be only opened with this FF bin viewer and SkyFit.
And the FR bin viewer, where is it?
The utils. So you need to use.
Okay, it's in the on the Raspberry Pi and the utils folder. Okay.
Yep.
Okay. Okay. I'll have to go and see.
Okay.
Thank you very much.
Is there a way to output the FR file as a GIF or AVI? Yeah, that's a good question. Right now, there's a manual command that I use that's on the group. I explained exactly how to do it. I'm just going to paste the link again. But we should at one point make a little script that does this automatically. We should definitely add that to the to-do list. And that's about it. Okay. Any other questions, suggestions, comments?
I'd have a suggestion. Sorry.
Sorry, go ahead.
Just a couple of suggestions. So Dennis did this presentation on the first part where he picked stars on about 38, 40 stars. I strongly suggest you use much more stars if there are enough of stars available. Cover the complete field of view. Do not hesitate to pick stars in corners, at least 3 corners if possible, because that asymmetry correction Dennis mentioned will not work as good as it can if you just cover diagonal corners. So pick at least 3 corners, as much stars as possible. Why? Because in some situations, catalog star positions are not quite correct ones. Either it's a binary star which is not covered with enough depth we have regarding limiting magnitude, and then you can have a couple of stars which are dramatically off, and you can't say the reason why. If you have 90, 100, 150 stars, you can easily live without those stars making a mess in your distortion model. So basically, do not try to fit plate pars on cameras which are inside the dome or using radial distortion, because you will end up with pulling your hair out from your head, because you can't do that with the radial distortions, because the distortion is simply not radial.
Yeah, so the point here the dummer is trying to make is the radial distortions work well if you just have the lens and maybe a flat glass in front of it. If you have the dome will introduce additional distortion that kind of breaks the assumptions that the radial distortion is making. So that then you need to use the polynomial fits. That is the main point. And we had a couple of issues with that. And I would say we do not recommend that cameras are deployed in domes after that, and that much higher precision can be achieved if we have just a nice flat glass in front of it.
Exactly so. And we introduced additional 2 models for polynomial distortion, which is not only poly 3 plus radial, it's now poly 3 plus radial 3 and poly 3 plus radial 5.
Which work okay.
Yeah. It's not kind of distortion that can be easily fitted. you should have more stars, but can resolve some tricky distortion or geometries you can face. Not only for our GMN RMS systems, but this SkyFit is now a tool which is really powerful one. And I don't know about any other tool which will allow you to do the astrometry the way this tool does.
Yeah, so one thing to say about SkyFit is always showing you how to do it with RMS data, but you can use any type of data produced by almost any meteor system right now. UFO, desert fireball network, or even any, some other professional cameras that we use here. As long as you can put it in some sort of a normal video format it can understand and make like a crude config file for it and give it the exact time, you can use any type of data. We use it for dash cams, for example, dash cam calibration, which is terribly hard, but it can be done. All sky cameras, many other things. It's something that you might not ever encounter, but it is possible if you really have to do it. Okay. Any other suggestions and things?
Yes, I have a question. Can I use a video file as input for SkyFit, or does it need to be pre-processed first?
Yep. You can use a video file as an input, no problem, just as it is, with a few extra things. You have to make a config file for it. And in the config file, you have to specify the name of the station, which I guess can be whatever you want. You have to specify the exact geographical coordinates, and again, specify an approximate field of view. And then when you're loading the video file into SkyFit, I can actually show you now.
Frame rate as well.
I'm going to share my screen though.
Then it's frame rate and the shutter type as well.
Yeah, but sometimes it can actually read the frame rate from the video file. But yeah, the frame rate should also be specified. So here I just ran SkyFit2 help, and the optional arguments are the time. So you see the beginning time of the video file in this format. The thing with FF files and other files is that you actually know the time is embedded into them. But if you just give it an arbitrary video, you have to give it the time, the exact time of the first frame. And of course, the frames per second, which sometimes it can read from the video file. But if you just give it a bunch of like images as video frames, then you have to specify the FPS, otherwise it won't know. So that's possible too. Yeah.
Okay, thank you, great.
Okay. Well, if there's nothing else, then we're gonna conclude. And if there are any other questions.
Yes, I have a question or a
Go ahead.
comment. What happened to me is that during the manual reduction process, I heard an amazing clatter of keystrokes, but I didn't necessarily know what keystroke was doing what. So you were adjusting the annulus, you were also moving back and forth. I don't know if there's any way to do this, but if there's some way to annotate the tutorial for just one set of common keystrokes during, it's obvious it's very repetitive, but that might be beneficial.
That's a great point. I know some like video recording programs that do have, they like annotate the exact keystrokes and they show it on the screen. I think this is great. I can just very quickly recap it now, if that's fine.
Oh yeah, that'd be great. Thank you.
So people understand. So let's do it quickly again. I'm going to share my screen.
Not quickly. Do it slower so we can see what we are doing.
Fair enough. So
when you press a key, tell us what key it is, I guess.
Sounds good. So I opened, I'm going to specify the command. Open the folder and tell it to do the FR files as well. I'm going to run this command. It's opening everything, FF and FR files. we already have a plate part file. We made a calibration before. We're going to load this now. The next thing is to find the exact image on which the fireball is. And here we can see the name of the file. It's this FF file, and we have this time here, and we just do left and right to switch between the files. And it's easier if I actually hide this text, but you can see it here. So I pressed F1. F1, if you press F1, it cycles between these windows here, labels here. So it's just gonna show everything initially. I press F1, hides everything. And this little snippet shows up, it says F1 show hotkeys. And I press that, and then shows the little kind of status panel, and then press it again, and you can just see the hotkeys. Okay, I'm just gonna hide everything with F1 again. So you can go left and right until you see the fireball. Now, what you see in the SkyFit window is the average stack. So you can switch between the average and the max stack by pressing the M like Mike on the keyboard. So you can see here I pressed M, and here this is average, this is max stack, right? So this is how you can kind of see the fireball and switch between these two things. When you're doing the astrometric calibration, you should always be using the average stack. But if you just want to see where the fireball is, you might want to switch to the max stack. So if I press F1, you can see here exactly which one is showing. It says this is a max pixel. If I press M again, this is the average pixel, right? So I located my FR file that I want to use. And after that, I switch to the manual reduction mode and just press this thing here. And it's showing here exactly the frame number we're on, the exact time. And now I can use left and right keys to switch between video frames. So I just keep hitting right. And let me just zoom this in for you. It's going to be easier. So just hitting right, just keep hitting right to get to see this, right? And I can go left until I just start seeing the fireball. So I just zoom in. I'm just scrolling my mouse, right? And here I am. So just kind of, I'd say this is the first usable frame that we can make our pick on. After that, I have to activate the picking mode, which is the same as the start picking mode in SkyFit. And I press Control R, R like radio. Okay, and I get this little annulus here. And then I can just again zoom in, and I click on this. I can adjust the size of the annulus if I have to, but again, holding Control and scrolling my mouse, and then it's gonna change the size of the annulus. I keep holding Control when I'm doing that, right? Once I'm done, I can just do this, click, and then I can either press left and right to go to change the frames, or if I would just want to go to the next frame, I can press space. So this big click that you just heard, this is space. And the reason why I did that is it's actually quite easy to do the picking with your mouse hand in one hand and to do your keyboard with the left hand, but without actually having to go across the keyboard. So everything is basically, you need like Control, Shift, Space, everything is on this kind of this side of keyboard. So I'm just gonna do click, space, click, space, click, space, click, space, click, space, and just keep going until you get to a part where you have to adjust your annulus, right? So what I did now is I pressed up and down is skip 10 frames back and forth. To skip 25 is page up and page down. You can actually see that here in, does page up and page down work? No, I think I removed that. It's Control left and right is 10 frames and up and down is 25 frames. It says right here in the little hotkey sheet. Okay, so here, when I come to the part when I have to change the annulus, again, just, move the hold control, adjust it, and I just keep on clicking until I get it. To remove a pick, you just right click on it. There we go. It's right click, right click, right click. And I think that's basically it. Once you're done, you hit Control S. It says right here, Control S, and you save it to disk. And that's basically it. I think we also have a couple of other cool options. Do we? No. To do some other things, and that's basically it. If you need to force a pick so it doesn't do a centroid. So for example, let's say that I'm centroiding this here. You see that like it doesn't really matter where I move my mouse, it's gonna kind of find a similar center of mass of this. But if I want to really force it in one spot, I hold Control and then click, and you see it's gonna be exactly where I click. So that's, sometimes you might wanna do that when the centroid doesn't go to where you want it to go. And I think that's generally it. I hope this was clearer than before.
Yes, thank you. It was very beneficial to really be able to track what we're seeing with how you're getting that motion to take place.
Yeah.
Thank you.
Yeah, great. No, anytime. I think that's about it, unless there's other questions that I'm willing to address. As you can see, we still have a couple of bugs here. The grade circle plotting is not ideal. We need to make some limits in the code, but yeah, generally that's about it. So perhaps as a final note, there are a couple of little things that I need to show you about SkyFit. I think that I just completely skipped that, and it would be good if I showed you. So, and this is the rest of these tabs here. So you've seen the levels tab, you know what that does. You can, change the levels and just this manually, which is great. The fit parameters, so you've seen it here. You should always, when you're fitting a plate, change to radial 5 odd. Make sure that refraction, equal aspect, and symmetry correction are turned on. These three here always need to be turned on when you're doing the fit from scratch, right? And you want to fit the distortion as well. These three here are central and radial 5. If the fit doesn't look good, when you press on this astrometry button here, you should go radial 7 or 9. And after that, we also have, for example, some station parameters, which just tells you the location of the station. You shouldn't really be changing this or setting this here. You should be changing this in a good config file. The config file is the central place, like a file that is never touched by RMS. So sometimes I get a question, oh, why don't we automatically update a config file in RMS, something? Well, I'm afraid that if there's a bug in the code or something goes wrong, the config file is going to be in a broken state. It's going to mess something up. The config file is only changed manually and never touched by RMS. If the config file is corrupted, something happens to it, it was not RMS. It was someone screwed up, or something's wrong with the file system or whatever.
Maybe it was Git.
That is a possibility. That's right. And finally, we have the settings. So I told you how we can change between the average pixel and max pixel, but you can also do it here, between the average pixel and the max pixel. Catalog stars, you can hide them. There you go. You can show and hide them, which is also pretty cool. You can also press the H button on the keyboard. It's going to do the exact same thing. It's all documented here on the side. There's show and hide detected stars. So in this particular case, I don't see the detected stars. I don't think we have them, but let me just open another, this one here. Let me just move this. Oops. Yeah, okay. So detected stars are those that are detected by the star detector, and they're marked by green circles, right? And in the settings, you can just remove show detected stars. You can see the little green circles appear and disappear. You can remove that. There's also show selected stars. So for example, when I make the pick and select a couple of stars, you can do this to remove that if you don't want to see them, right? There's another cool option, and that's show distortion. It can actually show you how the image is stretched from like the middle out. I think that's pretty cool, but that's just for effect. You can also invert colors if you like black and white and not the other way around. That can be useful sometimes. Some people prefer that. And measure ground points. Don't worry about it. This is when we're doing dash cam calibrations and pulling our hair out. You don't have to touch that right now. And you can also change the way which grid is plotted. Usually it's the RA and DEC grid. So basically, all lines are going to converge to the celestial pole, but you can also do the azimuth and elevation grid. So all the lines converge to the zenith, if you like that. You can also change the limiting magnitude here. So, let's say magnitude 6, you're going to see a lot of these tiny little small stars. And you can see this camera here has a really good limiting magnitude of, at least 6.5. And I usually keep that at like 5.5. There's no need to show those fainter ones. They're not even really good for like picking or anything. And finally, this filter rest standard deviation. When you're doing a photometry fit, sometimes you want to remove stars that are have like large residuals, and you can just tell it to give you stars which have like large photometry residuals. But here the problem is all of them are so good that there's nothing to remove. But as I said before, you don't really need to do the photometry anymore. Just set the vignetting coefficient to 0.001 in the plate bar file and forget about it. Don't even look at it. There's really no need. It's going to be recalibrated anyway. As long as the vignetting coefficient is fine, RMS is going to steamroll over your calibration when it's recalibrating the plate bar. So really, I'm not even going to discuss this. Just don't do it. And that's, I think, about it. That's most of the functionality that's in this software, and there's a couple of little things. Oh yeah, there's a little zoom window. So if you want to just look at it in the upper corner, for example, if I like kind of zoom in like that, but there's no need because you can zoom in the whole window. And that's about it. A couple of options here to like open a new plate bar, save a state file, load the state, or change station, which basically just opens a file dialog and just loads a different folder. But you can also do that from the command line. Just give it a different path. And I mean, it's a lot of redundant behavior. But that's a bit about it, I think. And yeah, there's one thing that I didn't discuss. This bottom status bar, you just move it around and you see exactly what the azimuth, altitude, right ascension, declination is below the cursor. And you also see, for example, what the image intensity is. You can see this intense parameter. And the way you know something is saturating, you just go in and check if the intensity is like 255. That's like 8 bits resolution. And this is not even saturated. I don't know if there's a single star here. There we go, this one here. 253. You see the intensity down there is 253, which is close to 255, which basically means that the star is saturating and its magnitude should not be trusted. But everything else has a lower intensity, and it's fine. Okay. I think we exhausted this topic, unless there are any other questions or comments or anything. Perhaps something in the chat. No, that's it. Okay. Well, thank you all for coming. Hope we can have more of these at some point if needed. I think this was a good update. I'm just going to upload this whole video to YouTube as it is. I'm not going to do any crazy cutting or trying to make it look nice. perhaps at some point we should sit down and have a nice thorough tutorial that's in one nice, say, logical order. If you ever feel comfortable with, doing that, please go ahead. That'd be great to have like a nice tutorial. And that's about it. Okay, unless there are any questions. Great.
Well, thank you very much. It was great. Much appreciated.
Thank you for coming.
No, thank you.
Thank you, Dennis.
Brilliant.